Hey everyone! In this video, we're going to walk through and solve some example problems that combine the tangential and angular descriptions from circular and rotational motion. Since these problems involve converting between the two descriptions of motion, even simple problems might seem harder than they really are, but they just involve a few more steps, and they'll get easier with practice. You can pause the video at the beginning of each problem and try solving it on your own first. Or you can just watch the video and see how we work through these types of problems. While a 30 centimeter diameter record is playing, a fly sitting on the outer edge of the record covers a tangential displacement of -28 meters during a song. How many revolutions did the record turn during the song? So what information are we given? Since we could be dealing with both angular and tangential variables, we'll have to be a little more careful about what the problem is actually telling us. First, we have a 30 centimeter diameter record with a fly sitting on the outer edge of the record. Let's start by drawing that out so we can keep everything in order. Here's a circle representing the record, with its diameter labeled as d, and a dot on the edge of the record representing the fly. Now let's write down the diameter, d, is 30 centimeters. Next, the problem says the fly has a tangential displacement of -28 meters. The variable for that is delta s. So let's write down that delta s equals -28 meters. Let's also label the picture. Since the displacement is negative, we're going to draw an arrow going in the clockwise direction and label it as delta s. Finally, the problem is asking us to find the number of revolutions that the record turns during that time. Revolutions is a unit of angular displacement, which is delta theta. So we'll write down that the problem is asking us to find delta theta in revolutions. Let's label our picture with delta theta too. Before we dive in, let's think about what we're trying to do here. We have a fly sitting on a spinning record. The record is in rotational motion, and the fly is in circular motion because it's traveling along a circular path. We're given a tangential displacement, and we're essentially trying to convert that into an angular displacement. In order to do that, we can use this equation, which converts between the two. But we need the radius of the circle. We're given the diameter, so you might just be able to do the math in your head, but let's write things out for now. The diameter of a circle is 2 times the radius, so now we have everything we need to find delta theta. Let's also label our picture with a radius r, which is just half the diameter. Before we start, we need to convert the diameter from centimeters to meters. To do that, we just divide by 100, and we get 0.3 meters for the diameter. Now let's start with this equation. We can replace r with d over 2, since the radius is 1/2 the diameter, and next we can rearrange our equation to isolate delta theta. Now we plug in the numbers we're given in meters, and that gives us -186.67 radians for the angular displacement delta theta. Remember that the conversion equation that we started with, delta s equals r times delta theta, uses the following units: meters for delta s, meters for r, and radians for delta theta. So if we plug in delta s and r using meters, we get delta theta in radians. This is beyond the scope of this video, but technically a radian is unitless, since we're dividing meters by meters to calculate it. You can think of a radian less as a traditional unit and more of a ratio of the arc length to the radius of a circle, which both have the same units. But for our purposes, when we use a conversion equation like delta s equals r times delta theta, all we need to know is that if we use meters for delta s and r, then delta theta will be in radians. But for this problem, it's asking us to find delta theta in revolutions. So we need to do one more conversion. If we multiply -186.67 radians by the relationship of 1 revolution to 2 pi radians, with radians on the bottom, then radians cancels out, and we get negative 29.7 revolutions for the angular displacement of the record. So that's probably the recommended way to solve this problem. Some of you might have thought about it differently, using geometry more than the kinematic equations. For problems involving position and displacement, there might be other ways to think about this conversion. So let's take a look, but feel free to skip to the next problem if you want. We already have our given information, but instead of trying to find delta theta, the angular displacement, we might think about it as finding the number of circumferences of a circle that the fly travels, which would tell us the number of revolutions that the record rotates. Here's the equation for the circumference of a circle, c equals pi times the diameter. If we use this and plug in 0.3 meters for the diameter, then the circumference is 0.3 pi meters, leaving pi in to be more precise. Conceptually, this circumference is the tangential displacement of an object traveling one revolution in a circle. So if the fly travels negative 28 meters, and one revolution corresponds to 0.3 pi meters, then we can divide negative 28 by 0.3 pi to get negative 29.7 revolutions, which is the same answer we got before. If you prefer solving problems like this using geometry, then feel free, but remember to keep track of your units and your positive and negative signs, since geometry doesn't usually include negatives. And if this method didn't make as much sense to you, then don't worry about it and just stick with the kinematic equations. Just like how using dimensional analysis to convert between units is good practice, using the kinematic equations usually lets us keep track of things a little bit better. But in later sections, using geometry will also be necessary, so it's important to know that too. A figure skater spins around with their arms stretched out and their hands 0.7 meters from their center of rotation. If the tangential velocity of their hands is 15 meters per second, what is the angular velocity of the skater in RPM? So we have a skater in rotational motion and their hands traveling around in circular motion with a positive velocity. Let's draw that out, with one of their hands traveling in a circle counterclockwise, since the velocity is positive. If their hands are 0.7 meters from the skater's center of rotation, that means the radius of their circular path is 0.7 meters. The tangential velocity, v sub t, is 15 meters per second. The problem is asking us to find the angular velocity of the skater, specifically in revolutions per minute, and we can label the picture with the angular velocity, omega. What equation can we use to solve this? Essentially, we're trying to convert from a tangential velocity to an angular velocity, so let's use this equation. We have the tangential velocity and the radius, so we should be able to find the angular velocity. Using this equation, we can rearrange it to isolate omega. Then, we can plug in the numbers we're given, since they're already in their SI units of meters and meters per second. We find that the angular velocity is 21.43 radians per second. Remember, when we plug in SI units using meters, the angular variable, in this case omega, will use radians. Does that answer check out? Actually, the problem is asking for the angular velocity in revolutions per minute, so we need to convert. Starting with 21.43 radians per second, we can multiply by the relationship of 1 revolution per 2 pi radians, so the radians will cancel out. That would give us revolutions per second. Now we multiply by 60 seconds per 1 minute, and the seconds cancel out on the top and bottom. When we multiply these fractions, we're left with 204.6 revolutions per 1 minute. So the angular velocity would be 204.6 RPM. Since the tangential velocity given to us is positive, then our answer for angular velocity should also be positive. A person is 6 meters from the center of a carousel, which is slowing down at the end of a ride. If the tangential acceleration of the person is negative 2 meters per second squared, what is the angular acceleration of the carousel? Let's draw a quick picture. While the carousel is rotating, the person riding on it is traveling in a circle, and the radius of the circle would be 6 meters. Their tangential acceleration is negative 2 meters per second squared, so the direction of the acceleration would be clockwise. The problem is asking us to find the angular acceleration of the carousel, alpha. What equation can we use here? This problem is very similar to the last one, but instead of working with velocity, we're dealing with acceleration. So we can use this equation to convert from the tangential acceleration to the angular acceleration, since we're given the radius of the circular path. First, we can rearrange the equation to isolate the angular acceleration, alpha. Next, we just plug in the values we're given. Negative 2 meters per second for the tangential acceleration, a sub t, and 6 meters for the radius, r. Using a calculator, we find the angular acceleration is negative 0.33 radians per second squared, which is the SI unit we get for the angular variable when using this equation. Should our answer be negative though? Well, the tangential acceleration is negative, meaning it's in the clockwise direction, and the angular acceleration would be in the same direction, so it should be negative too. A car on a 200-meter radius circular track is going 40 kilometers per hour. When the car is 60 meters from the finish line, the driver speeds up such that the car's angular acceleration around the track is a constant 0.02 radians per second squared. From the moment the car began accelerating, how long did it take to reach the finish line? There's a lot going on in this problem, so let's read that again and draw what the situation might look like. A car is on a 200-meter radius circular track. So let's draw a circle and label the radius r, and write down 200 meters in the given information box. The car is going 40 kilometers per hour, and at this initial point in the problem, the car is 60 meters from the finish line. So let's pretend the finish line is at the right side of the circle, and draw a dot representing the car, and an arrow between the car and the finish line. At this point, the car is going 40 kilometers per hour, so let's record that as the initial tangential velocity, v sub ti, and label the picture. The car is 60 meters from the finish line, so that means the car would travel a tangential displacement, delta s, of 60 meters to get from this initial point to the finish line. Since the velocity given to us is positive, and we're not given any other direction, we'll assume the car is traveling counterclockwise. Next, the problem says the car begins accelerating at this point, but we're not given a tangential acceleration, we're given an angular acceleration, alpha, of 0.02 radians per second. It was nice that this problem explicitly said angular acceleration, but if it didn't, we would still know because radians per second squared is the SI unit for angular acceleration. Finally, the problem is asking us how long did it take to reach the finish line. That means we're trying to find the period of time between the initial point, when the car is 60 meters from the finish line, and the final point, which is the finish line. Let's restate the situation looking at the picture that we drew. The car is at this initial point, where the dot is, and it has an initial tangential velocity of 40 kilometers per hour. At this point, the car begins accelerating, and it travels a displacement of 60 meters over some period of time to reach the finish line. So what equations can we use to help us solve the problem? Looking at the variables we're given and what we're trying to find, this first equation would probably help. Even though we're not given S final and S initial, we are given the displacement, delta S, so we know we can replace S final minus S initial with delta S. We're given the initial tangential velocity, v sub ti, and we're looking for the time, delta t, or in this equation, just t. But we don't have a sub t, the tangential acceleration. How can we find that? Well, we are given an angular acceleration and the radius of the circular path. So using this conversion equation, we can use r and alpha to find the tangential acceleration. Now we have everything we need to solve for t. As a side note, this kinematic equation uses the variables for the tangential description of motion. You might be asking, since we're given the angular acceleration, could we use the kinematic equation for the angular description instead? We definitely could. However, since we're given the displacement and initial velocity in the tangential forms, we'd have to convert two things into the angular form. If we use this first equation, we only have to convert one thing, the acceleration. So this one will be a little quicker to use. Alright, so before we begin, we'll want to convert the initial tangential velocity from kilometers per hour to meters per second. To do that, we can convert kilometers to meters by multiplying by the relationship of 1,000 meters per kilometer, and then cross out kilometers. Then we can convert from hours to seconds by multiplying by the relationships of 1 hour per 60 minutes and 1 minute per 60 seconds. We write these out so that the unit we want to cancel will end up on both the top and bottom of this list of fractions. So now we can cross out hours and minutes, and we're left with meters on the top and seconds on the bottom. Multiplying through, we get 11.11 meters per second. Let's write that over here so we have more space. For this problem, we're going to find it easier to plug in numbers early instead of rearranging the equation to isolate the variable we're trying to find, t. That's because, as we'll see in a minute, we can't actually isolate t on one side of this equation like we normally can. This is what's known as a quadratic equation, and we'll have to use the quadratic formula to solve for t, unless we have a fancy calculator with a solve function. For now, let's try and plug in all of the numbers we have. First, instead of replacing a sub t with r times alpha, let's just calculate it. We can plug in 200 meters for the radius and 0.02 radians per second squared for the angular acceleration. We end up with 4 meters per second squared for the tangential acceleration. Let's write that off to the side for now. Now we can take our kinematic equation and rearrange it by subtracting s initial. Now that we have s final minus s initial on the left, we can replace that with delta s, since they're equivalent. Okay, now let's plug in all of the numbers we have. 60 meters for the displacement, delta s, 11.11 meters per second for the initial tangential velocity, and 4 meters per second squared for the tangential acceleration. We can simplify the numbers on the right by multiplying 1/2 times the 4 meters per second squared. Also, since we can see that we've kept track of our units so far, and everything is in their SI units, let's drop the units to make things easier to write. We end up with this equation. 60 equals 11.11 t plus 2t squared, where the thing we're trying to find, t, is the only unknown variable. So it is solvable, but not using the normal steps because we can't isolate t. At this point, if you have a calculator with a solve function, you could plug this equation in to solve for t. If we do that, we find we actually get two values for t. Positive 3.36 seconds, or negative 8.92 seconds. Since we only deal with periods of time that are positive, then our answer for time would be the positive value, so t equals 3.36 seconds. Getting two answers might seem strange, but that's how a quadratic equation works. Both values satisfy the equation above. If you want, try it for yourself, first plugging in 3.36 for t in both places, and then again plugging in negative 8.92 for t in both places. Each equation will be true. What if you don't have a calculator that solves this for you? Then we need to use the quadratic formula. If we have an equation in this form, ax squared plus bx plus c equals 0, where a, b, and c are constants, meaning they're numbers, then we can solve for the unknown variable x using the quadratic formula. The plus or minus symbol means that x is equal to two different things, one where we use the plus and one where we use the minus. So, in order to use this, we need to rearrange the equation we have to match this form by subtracting 60 from both sides and then flipping the left and right. Let's replace x with t so it's easier to see how it applies to this problem. Now we can see that a is 2, b is 11.11, and c is negative 60. Keep in mind that the equation we're trying to match is adding each term, not subtracting. Therefore, we need to write it so that we're adding negative 60 instead of subtracting positive 60. Okay, now we can plug the values for a, b, and c into the quadratic formula to solve for t. We'll start with the plus version of the plus or minus symbol. When we do that, we get this equation. It's big, but we can plug that into a normal calculator, or we can simplify it in steps. But when we solve it, we get t equals 3.36. And then we can use the minus version of the plus or minus symbol. When we solve that, we get t equals negative 8.92. Those are the same values we got earlier, but we found them using the quadratic formula. Again, we only deal with positive time values, so our answer is still 3.36 seconds. You could double check that answer by plugging it back into the equations we started with, along with the given information, and make sure the math checks out. That was a longer problem, but it's not uncommon to have that many steps in a physics problem, so it's worth practicing. You turn up the speed of your ceiling fan from 150 RPM to 250 RPM. While the fan is increasing in speed, a fly sitting 80 centimeters from the fan's center of rotation travels a tangential displacement of 12 meters. What was the angular acceleration of the fan during that time? Alright, so let's draw a picture. We have a fly sitting on a ceiling fan traveling around in a circle. So we'll draw a dot on a circle representing the fly. The problem says the ceiling fan goes from 150 RPM to 250 RPM, so 150 would be the initial angular velocity, and 250 would be the final angular velocity. We could draw an arrow on the circle to show the motion of the fly, which we assume is counterclockwise because the velocities are positive. The fly is sitting 80 centimeters from the center of rotation, so the radius of this circle would be 80 centimeters. While the fly and the fan are accelerating, going from the initial to the final velocity, the fly travels a tangential displacement, delta s, of 12 meters. And the problem is asking us to find the angular acceleration, alpha. So to recap, the ceiling fan starts at an initial angular velocity, then experiences an angular acceleration, and reaches a final angular velocity. While the fan is accelerating, the fly travels a tangential displacement around the circular path. So what equations can we use for this problem? This equation will probably help since it has most of the variables we need. We have omega initial and omega final. We're looking for alpha, but we don't have theta initial or theta final, the initial and final angular positions of the fan. But we know that theta final minus theta initial is the same as delta theta, and the problem does give us a tangential displacement and the radius of the circle, so we can use this conversion equation to find delta theta, and then plug that into the top equation. So we have everything we need to solve this. Before we start, we'll need to convert the angular velocities from RPM into the SI unit of radians per second. We do that by multiplying the value in revolutions per minute by the relationship of 2 pi radians per 1 revolution, and then by 1 minute per 60 seconds. The units of revolutions cancel out, and so do minutes. We find that the initial angular velocity is 15.71 radians per second, and the final angular velocity is 26.18 radians per second. We also need to convert the radius from centimeters to meters. We do that by multiplying 80 centimeters by 1 meter per 100 centimeters, which gives us 0.8 meters. Okay, now we can use our equations. Starting with the acceleration equation, we can replace theta final minus theta initial with delta theta. Then we can replace delta theta with delta s over r. Now we can rearrange this equation to isolate the variable we're looking for, alpha. Finally, we can plug in the numbers we have for each variable using the SI units. When we calculate that, we find that the angular acceleration, alpha, is 29.2 radians per second squared. To check that value, you could plug it back into the equations that we started with, along with the given information, and then make sure the math is right. But let's just consider whether the sign is right. The ceiling fan went from an angular velocity of positive 150 RPM to positive 250 RPM. That means the change in velocity is positive. So the acceleration should be positive, which is what we got. Alright, thanks for watching, and I'll see you in the next video.